So today I'm going to discuss about Neumann architecture. What is that? So first, what is von Neumann architecture? It was proposed by the Hungarian-American mathematician and a physicist John von Neumann in the 1940s, and it has been become the foundation of most of the computers. So what is it? It is mainly a program stored memory. So what is that? Program stored memory is what in a memory we are having program and data. Okay, but in other architecture, in Harvard architecture, there was program and data uh, was separately stored in other memory. Means program was stored in a different memory and data was stored in a different memory. So in von Neumann architecture, it is a fundamental concept framework for designing and constructing digital computers. The contemporary computer is built on John von Neumann's concept of stored programs. Programs and data are kept in a distinct storage, as I told earlier. It is called memories in this stored program approach, and they handle the same. So this is the schematic diagram of a von Neumann architecture. First there is a CPU, central processing unit, and under that we are having control unit and arithmetic logic unit. And inside that, in the CPU, we are having some registers. First you can see PC, that is program counter. Then CIR is the current index register, then AC is the accumulator, MAR is the memory address register, MDR is the memory data register, or we can say MBR, memory buffer register. And next, this one is the memory unit. From input device, the CPU is taking the data and then the data is passed through output device. So in the schematic diagram, it is also known as IS computer and is made up of three fundamental components. First one is the CPU, second is the memory unit, and third is the input-output device. So in the CPU, central processing unit, it is the part of the computer that performs the bulk of data processing operations. That it is the brain of the computer system. So without CPU, we cannot do anything. Under CPU, we are having two components. One is ALU and another one is control unit. ALU performs the arithmetic and logical unit such as addition, subtraction, and or XOR, NOT, this type of things. And control unit means it is the control unit, means it gives the instruction and sends the control by sending the signal. So that is called the control unit. So control unit of a computer controls the operations of components like ALU, memory and input-output device. The control unit consists of a program counter that contains the address of the instruction to be fetched and an instruction register into which instructions are fetched from memory for execution. So now registers. Registers means it is a small memory that is in the CPU that store the content of execution for the CPU. So there are many types of registers. First one is MAR, memory address register, MDR, memory data register, AC accumulator, PC program counter, and CIR is the current instruction register. And what is the purpose of MAR? The register holds the memory location of the data that needs to be accessed. MAR means it is the address register. The data is the address is sent from CPU to memory, and in the case of MDR, the data is sent from CPU to memory and again from memory to CPU. So it can send and it can receive also. So this register holds the data that is being transferred to or from memory. Then AC is the accumulator. This register holds the intermediate arithmetic and logic results. Then PC is the program counter the register contains the address of the next instruction to be executed. Then current instruction register, this register contains the current instruction during processing. So this type of registers I have discussed earlier, so I am not going about the details of this. In previous lecture I have discussed about everything with an example, with a diagram I have explained that. So next is the buses. Buses means it is a collection of communication wax which are used to connect the components of a computer. If I am having CPU, then it is connecting with the RAM. Again, it is connecting with IO device, and this both are interconnected with each other. So that means this one is the bus. This is one bus. This is one bus, and this is the another bus. So there are three types of bus: address bus, data bus, and control bus. Address bus carries the address of data between the processor and the memory, not the data, only the address. And data bus carries the data between the processor, the memory unit, and the input-output devices. And the third is the control bus. It carries signals and commands from the CPU. Next is the memory. A memory unit is a collection of storage cells together with associated circuits needed to transfer information in and out of the storage. So memory stores the binary information in group of bits called words. So there are two types of memory. One is RAM and the one is ROM. Random access memory and read-only memory. So that was all about von Neumann architecture, and now I am going to tell about what is instruction. Okay. So instruction means it is the commands we are giving to CPU to perform some operation, that is only instruction. So here it is written a group of bits which instructs computer to perform some operation. So a group of bits means suppose this one is the digital computer, that is CPU. From this it is the input and this one is the output. So when we are giving some input to the CPU, we are getting some output. So what type of input we are giving? We are giving programs and data. Programs and data. Data means any kind of data we can give to the CPU and we are getting output. So group of bits means what? This one is the group of bits. This one is the program. This one is the program, and this one is the bits. So what type of program it is? It is a high level programming. It is a high level programming. So this program is a high level programming, and from this, using compiler or interpreter, we are decoding it using compiler or interpreter. So this one we are getting as an instruction. So this is the instruction. So these are the instructions. So from high level programming, we are converting it to low level language or machine language. We can machine language. So this one is the bit. So a program is transferred into a bit. So a group of bits which instructs computer to perform some operation, that is the instruction. Instructions are the basic building blocks of programs and define the specific task that the CPU must perform to carry out the program's operation. So this is the instruction format. Instruction format, this part, the left side is the opcode, that is the operation, we can tell as operation, and right one is the operand. Means in opcode, using operation means the operation is used to tell the CPU which type of operation you are performing, means addition, subtraction, and or what type of operation CPU will perform, that is denoted by opcode or operation code. And from where the operand will be fetched, means from memory, from accumulator, or from register. From where we will fetch the data, that is the operand, that is the operand's performance. So for example, a CPU supports 8-bit instructions. I'm just assuming it, that a CPU is supporting 8-bit instruction, assuming there is a 3-bit instruction stored in opcode. That means here only I am telling that it is a 8-bit instruction. It is a 8-bit instruction, and there is a 3-bit instruction stored in opcode. That means here in opcode we are having 3-bit. We are having 3-bit. Now, what will be the value? What will be the, how many bits will be there for operand? So for the operand, what will be the value? 8 minus 3, that means 5 bits. Five bits. So there will be 5 bits for the operand. Okay. Now there was 8-bit instruction. There was 8-bit instruction and 3-bit for opcode and 5-bit for operand. So this part is the operand part and this part is the opcode part. So how many combinations we can perform? We can perform 0, 0, 0 for 3-bit opcode, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0 and 1, 1, 1. So how many combinations we are getting? 1, 0, 0. Another one will be there. 1, 0, 1. 1, 0. So 8 combinations we are getting from 3-bit opcode. From 3-bit opcode we are getting 8 combinations. So when for a designer, the CPU will when CPU is designing the that time, what will happen, the designer will see that there are 8 types of combinations happening. For that, 8 type of operations will be there. So for 000, it can be addition. For 001, there can be subtraction. For 010, there can be move. For 011, there can be OR. For 100 and for 101, load. For 110, store. For 111, increment. So this can be the 8 types of operations CPU can understand. So you can tell that in 8-bit instruction, CPU can support 8 instructions, or CPU can support 8 instructions. Then CPU can understand the 8 type of instructions. Now, what is instruction set architecture? It is also called ISA. ISA, it is a set of rules and specifications that define the interface between the software and hardware in a computer system. It is a collection of all instructions supported by a CPU. Means what is that ISA? This one. All these things. Total 8. If in 8-bit instruction, if there is 8 combinations of instructions, this CPU will support this 8-bit instruction, that is only ISA. Collection of all instruction that is supported by a CPU, that is only the ISA. Next, types of instruction based on operation. So there are some operation based on data transfer. For data transfer, we are having some types of operations: move, LDI, LDA. For ALU, addition, subtraction, and or. For machine control, push, pop. Then for iterative, loop. For branch, JMP, call. All these things. Next, this is the main topic, that how types of instruction based on operands. Operands means that I have told in a data format that that right part is the operand part. So 3 address instruction, there are 3 address instruction, 2 address instruction, 1 address instruction, and 0 address instruction. So first one is 3 address instruction. Maximum 3 addresses can be specified within an instruction. First is opcode. Opcode will be there in every addresses. Then address 1, address 2, address 3. Means maximum 3 address it can be specified. It can support 2 address, it can support 1 address, it can support 0 address. But maximum is the 3 address. For an example, and R0, R1, R2. So these are the 3 registers and 3 address. For address 1, R0, address 2, R1, address 3, R2. So we are performing address addition. So in R0, I can perform the addition, that is R1 plus R2. So we can perform 3 address instruction like this. In next 2 address instruction, maximum 2 address can be specified within an instruction. First is the opcode, then address 1, address 2. It can support 1 address instruction, 0 address instruction. But the thing is, an example I am saying, suppose I am doing addition R0 and R1. Okay, so there is only 2 registers. Okay, so what I have to do, I am taking suppose R0, and in R0 only I am adding the R1. So what is happening? This R0 is acting as a source address and the destination address. Okay, and another disadvantage is that for the old value, means the R0 old value of R0 is overwritten by the new result. So when R0 value was, if the R0 value was 3, then and R1 value is 5. So when I am updating, when I am adding in R0, then the value is updated with 5 plus 3, 8. Okay, so the old value is being overwritten. So that is the drawback. Okay, then we are in the next lecture we will do this one address instruction. So in one address instruction, maximum one address can be specified within an instruction. One is opcode, another one is address 1. So address 1 means, suppose I am adding R1. So only one address is there. What I have to do? I have to take accumulator. So we will store the value in the accumulator. That is, implicitly we are adding in the accumulator. So this type of instruction is called accumulator based architecture. Next is zero address instruction. So no address is specified within an instruction, only opcode. So in this process we are having only push and pop. So this type of instruction is called stack based operation, stack based architecture. Stack based architecture. Now this is a question for you. Consider a digital computer which supports only 2 address instructions, each with 16 bits. If address length is 5 bits, then find the maximum and minimum how many instructions the system can support. So for this, what we have to do first, we have to draw the diagram, that is the instruction format. So this one is the instruction format, and it told about 2 address instruction. Means so here will be opcode, here will be address 1, here will be address 2. Okay, so 2 address instruction means opcode, then address 1, address 2, and each 16 bits, means the instruction is 16 bits. If address length is 5 bits, then address length is 5 bits, means these are the address. So this one is the 5 bits. This one is also 5 bits. Okay, this one also 5 bits. As it has told that address length is 5 bits. So what will be the value for opcode? Total is 16. Total is 16. So 16 minus 10. So remaining is 6. So opcode will be 6 bit. Opcode is 6 bit. Now what will be the maximum and minimum instructions it can support? So 6 bits means 2 to the power 6. What will be the value? 64. 64 instructions. Sixty-four instructions is the maximum instruction and minimum will be 1. Why? Because if it supports, if CPU supports 2 address instruction, that means it supports the instruction. So that is why 1 instruction will be there. That will be the minimum, not 0. In the next point, you can see, consider a digital computer which supports 16 2-address instruction. If address length is 6 bits, then the length of instruction is how much? So first of all, I have to draw the data format for 2 address. This one is the output. This one is the address. Address 1, address 2. And which supports 16 instructions. Means total instructions is not 16. It is 16 to address instruction. Okay. Then if address length is 6 bits, so how much you are getting the length? 16 means instruction is 16. Instruction is 16. That means how to get the value for opcode? We have to do log to 16. It has not told that 16 bit to address instruction. Look, previously it was told that each with 16 bits. But in this problem, which supports 16 to address instruction, that means the total instruction is 16. Now, how to get the value for opcode? Log to 16. That means it will be 4 bits. So, the value for opcode will be 4 bits. So, what will be the total instruction? Total instruction will be 6 plus 6, 12, and 12 plus 4, 16. 16 bits. So, answer will be 16 bits. It is not byte, it is only bits. If the question was in byte, then what I have to do? I have to do that will be 16 by 16 bits. That means 1 bit is equals to 8 byte. Sorry. 1 byte is equals to 8 bits. So 8 into 2 is 16. So 2 byte is 16 bits. So that time it will be 2 bytes. Okay. So in the next lecture we will learn about addressing modes. Okay. Thank you.